All right, let's talk about the inverse. So if two functions are inverses of each other, what they're going to do is they're going to undo each other, right? So if you look here, we have two functions, g and f. And if they're inverses of each other, we're going to say that g of f of a equals a and f of g of b equals b. So notice the g and the f, they canceled out and we're left with just the input, right? Our function notation, if I ever wanted to show you an inverse with notation, it would just be f to the negative 1 of x. So whenever you see this, you know that we're talking about the inverse. So if we wanted to think about an inverse in a real life perspective here, this, I know we've seen it before, right? This Dolbear function, right? So f is the temperature, n is the number of chirps, right? So if I want to figure out the temperature, I'm probably going to use this thing right here. Listen, how many chirps did I hear? Plug it in, run it through the function, see what f is, right? It's going to predict the temperature. But what if I wanted to work backwards? What if I wanted to predict the number of chirps and I actually knew how hot or cool it was, right? What I would need is I would need the other side of the coin. I would need the other function going the other way. I would need to have a function that was based on f and not n. Right now this function is based on n. So what I would need is I would need a function built on f, or how hot it is, and that would give me n. Now this function, if I type in an n, it should give me a specific f, right? If it were 16 degrees, it would be 44, or if I heard 16 chirps, excuse me, it should be 44 degrees. It should work backwards too. I should be able to type in 44 degrees in here and get 16n, right? So both this needs to be a function and this needs to be a function. The two need to be functions together. So the original and the opposite side of the coin both need to be functions. And if that happens, then the inverse exists. So let's look at this real quick. There's two perspectives, right? There's two sides of the coin. Y equals f of t and t equals f inverse of y, right? So here the input is t and the output is y. Versus over here in the inverse, the input is y and the output is t. It's just going, am I going from chirps to degrees, or am I going from degrees back to chirps? That's all you need to be thinking about here. So let's figure out if these are going to have inverse functions, right? So the first one is this graph right here. Would this graph have an inverse? I would say yes, it would, right? Because I go over here to A. So let's say that I heard 13 chirps, that will spit out how hot it is. And if I hear 18 chirps, that'll spit out how hot it is, right? Versus if I go, how hot is it? And then kind of find my way back to the number of chirps, it'll still be kind of a one-to-one correspondence. Over here, on the other hand, this is a little different. I would say that this function does not have an inverse. And the reason why is because, let's use my chirps again, right? Let's say I heard 13 chirps, right? Okay, that means that it's however many degrees, 18 degrees, 37 degrees, whatever. And then I heard a couple more chirps, and that could also lead me to the same temperature. That's not a problem. The problem is when I work backwards. What if I knew the temperature was 80 degrees? Well, 80 degrees would, if I tried to find out how many chirps there were, it would bring me back to two inputs or two chirpings, right? And that's not good. That needs to be a function as well. So this one will have an inverse. I'm good with that. This one will not have an inverse. And the reason why is because the output gets mapped to two inputs. So remember, a function passes the vertical line test. If I want to see if its inverse exists, I have to make sure that the original function passes the horizontal line test. And I know that's something we talked about in Algebra 2 last year. So the horizontal line test, a function whose graph lies in the xy plane has a corresponding inverse function if and only if every horizontal line intersects the graph at most one point. So if we look back to here, I could see that this one, because this is my original graph, it is a function, passes the vertical line test, and its inverse is also a function because it passes the horizontal line test. This one, on the other hand, it's a function, passes the vertical line test, but its inverse is not a function because it doesn't pass the horizontal line test. Whew, man, it's good stuff. So let's see if these are our last two problems of the day. So let's see if these things have a function that's or an inverse that's a function, right? Does this thing right here have an inverse that's a function? Does this one right here, there's two of them, r of t and s of t, do they have inverses that are functions? And if they do, we'll find them. And if they don't, well, I'll show you why they won't. Real quick, here's the graph of the first one. So if you look here, when I look at this, I can see that it passed the vertical line test, so r of t is going to be a function. And it also passes the horizontal line test. So I can see that r inverse of t is also going to be a function. So I have a hunch that this is going to work, that this one is going to have an inverse, right? And then if I look at s of t, I have a hunch that this one is not going to work because, again, it passes the vertical line test, but it does not pass the horizontal line test. So I'm going to say that s negative 1 of t, or s inverse of t, is probably not a function. Let's check it out. Oh, dang, I missed one. That's okay, we'll work there. So we start off with y equals, we're starting off with this one right here, right? So I'm just going to show you how to do the algebra. It's always good to know. 3, so the first thing I need to do is I need to flip-flop my input and my output, right? Because we're trying to flip-flop this function. We're trying to make the input the output and the output the input. And then what I need to do is I need to solve for the y. So I'm going to go ahead and I'm going to subtract 3 from both sides. I got to get rid of this negative 1/5, so I have to multiply by 5 on both sides, right? And then I have to get rid of this cubed root, so I have to take the cubed root of both sides. I also distributed the negative 5 in here and in here. And then finally I have to add 1 to both sides. So this is my new inverse function, and showing you correct notation, it would be r inverse t equals this thing right here. Notice a cubed root, that's going to be fine. We're only going to get one output here. Not a big deal, right? So this one is actually going to be an inverse, and its inverse is this right here. Now if we compare that to this guy, s of t, again, we got a flip-flop, so I'm going to write the t where the y was and the y where the t was, and then I have to solve for y. So I'm going to go ahead and I'm going to subtract 3 from both sides. I have to get rid of the negative 1/5, so I have to multiply by negative 5 on both sides. Nope, you can't see it. Maybe you can. Nope. It's down there. I guess you'll have to trust me. I multiply by negative 5 on both sides, and then I have to take the square root of both sides, right? And remember from Algebra 2 and Algebra 1, whenever I take the square root or a fourth root or a sixth root or any even root, it's going to have that plus or minus that follows it. So the problem with this is, and I get this, so s negative 1 of t equals 1 plus or minus the square root. So here, if I have an input of t, I'm going to have two different outputs, and that's going to be a problem, right? So this one, actually, the inverse does not exist. This mathematically is the inverse, right? But since it doesn't pass the test, the horizontal line test, we're going to say that it doesn't have, or that the inverse does not exist. Okay, so that should get you going. With inverses, we're going to hit the ground running on Thursday. Peace.